Hey everybody. Well, I hope and pray you're all doing well here in the midst of the coronavirus pandemic in spring 2020. In this video, I'd like to go over some old Calculus 2 exam problems that I've given to my students at Bethel University in the past for the benefit of current students, future students, and anybody else who happens to be watching. These problems are going to focus on two main areas: applications of integrals and then also series, both looking at when do series converge or diverge, and also Taylor series. The applications of integration are going to be to some volume problems, to some physics. Then we'll do an application of sequences in series to finance, present value and future value, before getting into the more abstract stuff. At the very end, I'm also going to do an application to actuarial science that's not part of a standard calculus curriculum. Don't worry about the numbering and the point totals. I'm just taking these off of old exams. It's somewhat random what you're going to see there as far as the numbering goes. This very first problem, we're going to find a volume of a solid of revolution. We're going to take a two-dimensional region in the plane and rotate it around the x-axis here. We do rotate this region between y equals 1 and y equals x squared, two graphs, for x between 1 and 5 around the x-axis. I also wanted my students to make sure you draw either a three-dimensional picture, which is kind of tough to draw, but you can do your best, or the head-on cross-sectional area that you would get by slicing the three-dimensional solid perpendicular to the x-axis. Okay, so let's go ahead and get started on this. It is a good idea to try to make a little drawing first. Take note of the fact that I'm doing more than just drawing these curves, y equals 1 and y equals x squared. I'm also thinking about an interval of values. X goes between 1 and 5. That's important to pay attention to. If I only said between those two curves, say in the first quadrant, then x would go between 0 and 1. But here I want x to go between 0 and 5. Let's say 5 is right about here. This is the two-dimensional region that I want to rotate around the x-axis to create a three-dimensional solid. Again, it's not a real easy thing to draw such a solid, but we can do our best here in a short amount of time. I'm imagining rotating this around the x-axis again. What I'm going to get is a three-dimensional solid that looks about like this, okay? It's sort of like a cone on its side with a hole in the middle here. I'm not the best artist. I used to draw a lot more than I do now, but here we go. Something about like that is the three-dimensional solid with a hole in the middle. That's the thing we want to try to find the volume of. We do it by slicing. Imagine taking a knife and cutting this perpendicular to the x-axis. So here's the x-axis, here's the y-axis. Cut this perpendicular to the x-axis into slices. And remember, there's a hole in the middle. So each individual thin slice is going to be shaped like, well, it's often called a washer. If you look at it, I'm not sure if my head's going the right direction for you. From the right, looking head on, the cross section is going to look like this. It's sometimes called a washer, as in a washer you use in plumbing, because it's a ring shape. Okay. You could also, the more official name for this in math is it's called an annulus. It's the region between two circles, centered at the same point. There's an inner circle that's got a smaller radius. Let's call that r sub in for inner circle radius. And an outer circle that's got a bigger radius. Let's call the radius of that r sub out. Okay? So we're looking at this head on. That's what the cross section looks like. How do you find the answer? We need to figure out how this cross-section, how its area depends on x. That's the key, initial step. And then the second step after that is to integrate the function. Integrate that cross-sectional area function. That can be justified with Riemann sums or infinitesimals. But let's just go ahead and jump to what you do. We need to take the area of this thing, which is going to be the area of the outer circle, pi times r out squared, minus the area of the inner circle, pi times r in squared. But both r out and r in depend on x. As x increases in this picture, the washer gets bigger. The annulus gets bigger. The area depends on x, and in fact, as x gets bigger, the area gets bigger. Both r out and r in depend on x. How do they depend on x? Well, remember the x-axis is the axis of rotation. R in is going to be the vertical distance from the x-axis to this point right here, which is on the line y equals 1. R in is actually constant. It's always equal to 1. R out is what changes. It's the distance from the x-axis up to this graph right here. But that graph is y equals x squared. So R out is x squared. So this equation, I'm going to go ahead and factor the pi out, becomes pi times, in parentheses, x squared squared minus 1 squared. Pi times x to the 4th minus 1. That's the function we need to integrate from 1 to 5 to find the answer for the volume. The volume is the integral of the cross-sectional area function. X going from 1 to 5 in this case. Okay? So if that doesn't seem like it's a problem to you, go ahead and jump ahead to the next problem or something, which will be another volume problem, but with particular kinds of cross-sections that are actually not washers. But if you want to go ahead and see the answer to this, go ahead and do the integral here. Integral of x to the 4th is going to be 1/5 x to the 5th. Integral of 1 will be x. Fortunately, I'm evaluating from 1 to 5. I'm not evaluating from 0 to something, so it's a little bit more work. And I think I'm going to feel safe here, I'm going to want my calculator. Got pi on the outside. 5 to the 5th divided by 5 is really 5 to the 4th. 5 to the 4th is 625. 5 to the 4th is 625, yep. Oops, 625 minus 5. Subtract from that 1 to the 5th over 5, which is 1/5 minus 1 itself. So it looks like we have 620 plus 1, 621, minus 1/5 will be 620.8 times pi. Okay? If you're trying to write that as an improper fraction, so to speak, what would it be? 620 times 5 is 3100. Add on another 4 to that because of the 0.8. This is going to be the same as 3104 pi divided by 5. Would be another way to write that. Okay? And what does that equal? As an approximation, it's approximately a volume of 1950.3. Okay? And units, if you were asked for units, would be whatever units of cubic length you're talking about. If you're working in meters here for the length, then that would be in cubic meters for the volume. All right, the next problem is also a volume problem. Find the volume of the solid, still a volume of a solid, over a region, x going between 0 and 2. Between the graph of y equals 0 and y equals x squared is what that means. Between those two graphs, y equals 0, of course, is the x-axis. We're not rotating that region. The cross-sections perpendicular to the x-axis are semicircles. Okay? By over the region, I mean here the base. The region is the base of the solid. This is the base of the solid. So sometimes you'll see the problem phrased that way. Make sure you either draw a three-dimensional picture or the head-on cross-sectional area as part of your work. Okay, those instructions to my students. So the two-dimensional region that is the base of this three-dimensional solid should be drawn first. X goes from 0 to 2. Y is between 0, which is the x-axis, and x squared. This is our region of interest. This goes up to 4 here. That's the base of our three-dimensional solid. I actually have not drawn what the instructions say to draw yet. Here would be what the three-dimensional picture looks like. Imagine the x-axis kind of coming out of the paper a little bit there. the y-axis going into the paper, and a third axis, say a z-axis, going straight up. This region in the xy plane, where x goes from 0 to 2 and y goes from 0 to 4, with perspective might look about like that. The cross sections are what I get when I do the cutting. For any given value of x, the cross section is a semicircle whose diameter is this length right there, from y equals 0 to y equals x squared. And that's going to help us find the cross-sectional area. These semicircles get pretty small when x is close to 0 because there's not much length there. When x is close to 0, the length here is pretty small, which makes the diameter pretty small. It makes a pretty small semicircle. It's biggest when x is 2. So this is the three-dimensional solid you could draw. If we were thinking about the cross-sections themselves, again, they are semicircles. That's where you're looking at this three-dimensional picture head-on, and you're thinking about making a slice and looking at one of those slices there. That's what the head-on picture looks like, a semicircle. A certain radius. Let's call the radius r. The area is ultimately a function of x because r is ultimately a function of x. The area of a circle is pi r squared, so the area of a semicircle is 1/2 pi r squared. R depends on x. And how does r depend on x? Well, the diameter is the distance between 0 and x squared. In other words, it's x squared. Half of that is the radius. So r is x squared over 2. Simplify this, that'll be the function we have to integrate. It'll be 1/8 pi x to the 4th. That'll be the function to integrate to find the volume. So the volume is the integral of this cross-sectional area function. Again, this can be justified either by thinking about Riemann sums or infinitesimals, but that's not my purpose here. Our purpose is just to get to the answer, to show you how to think about it and solve. Integrate this, you're going to get pi over, let's see, 8 times 5 is 40. Pi over 40 x to the 5th going from 0 to 2. That'll be a little nicer because when you plug in 0, you get 0. 2 to the 5th is 32. 32 pi over 40. 32 and 40 are both divisible by 8. This is the same as 4 pi over 5. 0.8 times pi. About 2.51 cubic units. Okay? That is problem number 2. And that's the last of the volume problems. Let's move on to a physics problem. The mass density of a thin rod is given by this function. Delta of x equals x squared plus 4. It's a thin rod, effectively like a wire maybe, a really thin wire, though it's somehow stiff. And the density is not given in the usual units. It's not units of mass per unit volume. It's units of mass per unit length, because effectively you can treat the thin rod as one-dimensional. It's an oversimplification, okay, for the sake of being able to get an answer more easily. For x going between 0 and 3. Before we get into solving this, let's think about what that means. So it's a thin rod, like a wire or something, some sort of stiff wire. I guess it doesn't have to be stiff, it could be flexible. The units of x, our units of length, would be centimeters. You might want to draw an x-axis down here, where this is x equals 0 and this is x equals 3. And according to that particular scale, the density is this function. It's not constant. Kind of strange. Could you make such a thin rod? Well, if you can, I'm not sure how, but we're pretending for the sake of illustrating the ideas. The idea about what this density means is if you make a tiny little cut in this thin rod somewhere of a certain tiny width, call it delta x or dx if you prefer, the mass of that tiny little length, you could call delta m, would be delta of x times delta x, lots of deltas, okay? Delta of x is the function giving us the density. Delta x, capital delta, is the change in x. Delta m, capital delta, is the change in mass, or maybe the small mass is another way to think of it. And again, you could also write this with infinitesimal notation. You could write dm equals delta of x dx, and you'd be thinking about these as infinitesimally small quantities. It's an intuitive way to approach things, but you don't have to. So, you know, if x happened to be about, well, 1 there, the mass of this tiny little piece you'd cut out, you'd find by plugging 1 into this function to get 1 squared plus 4 is 5 grams per centimeter. 5 times that tiny length, whatever that tiny length happens to be, would be the mass. If the tiny length were 0.01 centimeters, then 5 times 0.01 is 0.05 grams would be the mass. To find the total mass, you add up the little masses. In other words, you integrate the density function. Okay? Integrating the density function is essentially adding up the little masses. You think of the integral intuitively as adding, going from 0 to 3. Now, of course, to do the integral, you don't literally add anything. You use the fundamental theorem of calculus, which is, you know, amazing that this works. Find an antiderivative of that and get 1/3 x cubed plus 4x. X goes from 0 to 3. 3 cubes 27 divided by 3 is 9. 4 times 3 is 12. I plug in 0, I'll get 0. This is 21 grams would be the total mass of that thin rod. All right, that's pretty nice. What about the center of mass of the rod? Center of mass, location. Okay, well, you got to know the formula for that. It's written sometimes as an x bar. And when the density is, in this linear situation, the formula for the center of mass is the, it's called the moment of the thin rod in the x direction divided by the total mass. What is a moment? Well, it's not a moment in time. It's kind of confusing terminology. I don't want to get into details about it. It's related to something called the law of the lever in physics. You find the moment by integrating x times the density function. And actually, if this were a probability problem and this were a probability density function, that would be all you have to do because the mass would be 1. But now, this is not a probability problem, it's a physics problem. We got to divide by the mass we just found, 21. And let's see, so we'll be integrating x times delta of x, we'll be integrating x cubed plus 4x. Divide by 21, do this as fast as I can. Get 1/4 x to the 4th plus 2x squared from 0 to 3 divided by 21. 3 to the 4th is 81. 81/4. 3 squared times 2 is 18 divided by 21. Getting a common denominator up top of 4, that's 81 plus 72 over 4, all divided by 21. 153 divided by 84 is what this looks like if I have not made a mistake. Actually, I don't know for sure that I haven't made a mistake. 153 divided by 84. 1.82 centimeters would be the location of the center of mass. Maybe actually I should just double check that I didn't make a mistake with my technology here. I use Mathematica a lot. I'll use that here just to double check that I did not make a mistake with this integral on top. So integrate 0 to 3 x cubed plus 4x dx. Okay, 153 over 4, then I divide that by 21. Yeah, would be dividing by 84. Okay, so it looks good. Next problem, more physics, related to the work done by a force in the form of a water tank. And sorry, we're not using metric units here. I will talk briefly about what it would look like if you were using metric units. If you know what to do here, it's actually a little easier when you don't use metric, though you do need to know what to do. So it's a water tank. in the form of a right circular cylinder, in other words, a can shape, with a height of 10 feet and a radius of 6 feet. Okay, so I'll make a drawing here in a minute. The tank starts half full of water at the start, before you're pumping the water out. Find the work. This is a physics concept, and it's not the everyday concept of work, required to pump all of it over the top rim. Work is really equivalent to energy here. How much energy is expended? Now, in standard metric units, the energy units would be joules. Here, in using these units, the energy would be in what is called foot-pounds, feet times pounds, effectively. Okay, let's go ahead and draw the right circular cylinder here, which is a can shape. That is our tank of water here. We also will need to use the fact that the weight density of water is 62.4 pounds per cubic foot. Okay, and actually having that as a weight density is kind of nice because that's already a force. It's not a mass, it's a force. So our tank is 10 feet high and a radius of 6 feet. 10 feet high, radius of 6 feet. I guess we're going to use purple water here. It's starting at a depth of 5 feet. So that's 5 feet there. But then we're pumping water out. I think I had a physics teacher justify this for me once. So we're going to be putting a hose into this tank and sucking all the water out, pumping it out up to the top. So it's like you've got some sort of pump here. I don't know how to draw a pump. Okay, some sort of machine here with a hose going in. And, it's going to be sucking the water out, and you probably do want the hose to be at least 10 feet long. So the water, you don't want to think too carefully about this is sort of the main point I'm going to try to make here. What's really going on is you've got the water molecules flying all over the place inside this fluid, and they're getting sucked down toward this hose before they get sucked up to the top of the rim there. So their motion is up and down. So how in the world would you possibly think about the work done by this as you pump all the water through the hose where the water has to go down first before it goes back up? Work is, in general, when you've got a constant force, it's a force times a distance. How in the world can you possibly calculate such a thing? Yeah, like I said, I think I had a physics teacher justify this to me once, but what you can do is you can oversimplify it. You can think about thin slices of the water. Here's this emphasis on slices in these applications of integration again. And think about the vertical distance against gravity those have to go, that the thin slice of water has to be pumped up, okay? The net vertical upward displacement. Not worrying about the fact that the individual water molecules are flying all over the place and have to go down first and that kind of thing. It's the net work against gravity, and evidently if you think about the thin slices and add up the work required to move each thin slice up to the top, it's going to give you the right answer anyway. And again, ask your physics teacher to completely justify that. All right, so how do you have to do that? Well, for a given thin slice, let's call this direction y, and this will be y equals 0 down here at the bottom of the tank. For a given thin slice at height y, don't be fooled by the fact that I'm using a y both as a label for the axis and a particular value here. It's not a big deal. How far does that thin slice have to move upward? And what's the force that's required? If I could find those things, I could multiply them, and multiplication would be good enough because this slice is so thin that effectively all the water in it goes about approximately the same distance upward. So again, this is why this distance here, if you think about it, with the fact that the total height is 10 feet, is going to be 10 minus y. So that's the distance in the work equals force times distance equation. What is the force, though? So let's write it. So let's call the total work delta W for the thin slice here. I could call it dW if I thought of this as an infinitesimally thin slice. That's going to be approximately, say, since it's technically got a little bit of thickness to it, the force times the distance. What's the force? Let me call it delta F initially. Delta F, the distance is 10 minus y. Well, what is force? It's mass times acceleration, you could say, kilograms times meters per second squared if you're using standard units, which in standard units is called newtons. In non-standard units like this with feet and pounds, the force is the number of pounds. Okay? Number of pounds. Now again, the water weighs 62.4 pounds per cubic foot. So this delta F is really 62.4. This is in pounds per cubic foot. Another funny thing is this abbreviation for pounds is LBS for some reason. Pounds per cubic foot times the number of cubic feet. This radius has got to be relevant somehow. Call that number of cubic feet, well, delta V initially. That's in cubic feet. Times 10 minus y. We now want to figure out what delta V is in terms of y, because we're going to integrate with respect to y. And this is going to be in feet. The final units are pounds times feet, foot-pounds. I could write it as feet times pound as well. But what is delta V? It's the volume. It's a cylinder. Pi r squared times the height. 62.4 times pi. The radius is constant. 6 squared is going to be r squared. What's the height of this thin slice of water? Well, I suppose we should call it delta y, right? Think of y as a fixed number, but delta y is the tiny width of this. Delta y is what I'm trying to draw there. And then don't forget about the 10 minus y. So these are the little works in foot-pounds that we have to add up, so to speak, to get the total work. And the integral does the adding. The total work is the integral of what? Well, it's this times this, and it's kind of like the delta y changes into a dy, almost as if by magic. It's not really magic. It's the definition of the integral involving Riemann sums, but it kind of seems like magic. 36 times 62.4, 2,246.4, 2246.4 pi, don't forget the pi, times 10 minus y, dy. It's as if the delta y has morphed into a dy like by magic, but again, it's really not magic. Y goes from what to what? Well, y goes from 0, the bottom of the water, to 5, where the top is. So this is the integral from 0 to 5. Okay, a little bit of a pain, but doable. 2246.4 pi. Integrate 10, you get 10y. Integrate negative y, you get minus 1/2 y squared. Y going from 0 to 5. Fortunately, when you plug in 0, you get 0. 2246.4 pi. 50 minus, let's see, 25, 5 squared is 25 over 2 is 12.5. That's a 37.5. So we have 2246.5 times 37.5 comes out to 84,243 times pi. 4,243.75 times pi foot-pounds. And again, I hope I have not made a mistake. You know, I do make mistakes, so it's possible. I think I remember this is the correct answer approximately. Approximately 264,660 foot-pounds. 264,660 approximately. foot-pounds. What would you do if we were using scientific units, standard SI units? You'd be given, maybe 10 meters and 6 meters. You wouldn't be talking about the weight density of water, you'd be talking about the mass density, which is almost 1,000 kilograms per cubic meters. It's a little bit less. The main thing you'd have to do differently after that point is to find the force, you'd have to multiply by 9.8, the acceleration due to gravity near the surface of the Earth, turns out. Okay, so besides doing everything else the same with 1,000 instead of 62.4, you'd also have to multiply by 9.8. Your final units would be in joules when you do that. Essentially, newtons times meters is joules. All right, assuming a continuously compounded interest rate, R equals 4% per year over 5 years, find the present value at time 0 and the future value at time 5 of what's called a discrete annuity. An annuity is just a series of payments. 5 payments of $1,000 made once per year, starting immediately at time 0 and ending with the last 5th payment at time 4. So the payments are at time 0, 1, 2, 3, and 4, which is 5 payments. You can imagine these things with a timeline, if you like. These are the times and years that go by. Your payments are at 0, at 1, at 2, at 3, and at 4. All right. The basic equation we need, initially at least, is the formula for compound interest when interest is compounded continuously. You could write that as A, the amount, is as a future value, the initial amount deposited times e to the continuous interest rate, R, times t. That's going to give you the future value, FV. You can also solve that for the present value, the starting value, A0, present value, by dividing both sides by e to the RT, which is the same as multiplying both sides by e to the negative RT. But we're not just doing this for one deposit, one payment, we're doing it for 5. So I need to do 5 of these things, both for present value and future value. Yeah, that doesn't sound so pleasant. Why did I do such an unpleasant problem? Well, it's actually less unpleasant than you might think. Okay, it's not as bad as it seems at first if you know the formula for a finite geometric series. So we're getting into series now. Problems that come after this are going to involve tests for convergence or divergence, and then also Taylor series. So the future value, or let's do the present value first. Present value total is going to be, well, first of all, the value of 1,000 at time 0, which is itself, because no time is going by with that one, plus the present value of 1,000 at time 1, back at the present. What is the present value of that one, 1 year in the future? I've got to use this formula with A equal to 1,000, R equal to 4%, which was 0.04. I have a negative RT, and T is 1. That's a times 1 there. Next one would be 1,000 e to the negative 0.04 times 2 for the one at time 2. Oh, I guess I might as well go ahead and write all 5 of them out. Plus 1,000 e to the negative 0.04 times 3. Plus, finally, the last one is 1,000 e to the negative 0.04 times 4. Present values are smaller than 1,000, at least for the ones after the first one. When you have e to a negative power like this, you're going to get numbers less than 1 that you're multiplying 1,000 by. These are going to be probably mostly likely 900 something for these things, maybe down into the 800s. The total present value is going to be less than the sum of all these. It's going to be less than 5,000. Now you can go ahead and take the pain of plugging all this in your calculator, but you should know, and my students should know, that if I made this 20 payments instead of 5 payments, you should still be able to do the problem. And maybe I will for you. So you've got to know the formula for the sum of a geometric series. And this is a finite geometric series. You've got a leading term, 1,000. And then you've got a common ratio. What do I need to multiply each term by to get the next term? Etc. E to the negative 0.04 is the common ratio. So it's the leading term. Let me go ahead and write it in words here. Leading term times 1 minus the common ratio. This says common ratio. Those m's are hard to see. Common ratio to the power equal to the number of terms, all divided by 1 minus the common ratio. That's the general way to remember it. That's a good way to remember it in general. Okay, and I was thinking common ratio there, and I almost wrote a fraction. Ratios are fractions, right? Often that's how we think of them. So 1,000 is the leading term. Common ratio is e to the negative 0.04, and there's 5 terms. So that would be the same as e to the negative 0.2, actually. This thing here is equal to, multiply those exponents, e to the negative 0.2. And then divide by 1 minus the common ratio. Divide by 1 minus e to the negative 0.04. Okay, again, you should be able to do that even if I had 20 terms. What would change? The only thing that would change is this 5 would become a 20. Okay? You should be able to do it still, instead of doing this stuff out. I want you to know the formula for a finite geometric series and an infinite geometric series at that as well, at least convergent one. Let me calculate the bottom first. 1 minus e to the negative 0.04. Oops, mistake. 1 minus e to the negative 0.04. That's what the bottom is. Now let's calculate the top. 1,000 times 1 minus e to the negative 0.2. And I'll go ahead and do the division right away as well. Well, you might want to do that so you can write it down so you can get more partial credit. Now go ahead and divide 0.039210568. If you write more things down, if you make a mistake, it's easier for me to find your mistakes, and that can give you more partial credit if you do it right, but just make an arithmetic mistake. So this is about 4622.97. It is less than 5,000. And the point about this present value of this annuity is that if you had received a one-time payment of this amount at time 0, instead of these 5 payments of 1,000 at time 0, 1, 2, 3, and 4, these are equivalent as long as you got a 4% interest rate available to you for your investment. So that's good to know. Okay, it's good to also, another application of this is maybe you want to pay somebody to give you this money in the future. How much should you pay them now to give you this amount of money in the future? Which, I mean, of course, it seems kind of silly for them to give you $1,000 right away after you've already paid them this amount at the start. But it can help you think about how much an annuity is worth to you. All right, so that's the present value. What about the future value in total? Now I need to take all these amounts and bring them into the future to time 5. So this one needs to get multiplied by e to the 0.04 to the 5th power, which is equivalent to this here. 0.04 times 5 would be 0.2. Then with this one, I'd have e to the 0.04 times 4, equivalent to e to the 0.04 to the 4th power. I'm going to get 1,000. E to the 0.04 times 5 is e to the 0.2. Plus 1,000, e to the 0.16, plus 1,000, e to the 0.12, plus 1,000, e to the 0.08, plus the last payment at time 4 goes 1 year into the future, so multiplied by e to the 0.04. All these e's to positive powers are bigger than 1, so these numbers are bigger than 1,000. You add them up, you get bigger than 5,000. But it's still a geometric series. I can still use this formula, leading term times, in parentheses, 1 minus the common ratio to the number of terms power, all divided by 1 minus the common ratio. The leading term now is 1,000 e to the 0.2. The common ratio is actually the same as e to the negative 0.04. Why? Because that's what you have to multiply by to get the next term each time. Alternatively, thinking of it as a ratio, I could take any term except the first one and divide by the preceding term, and I would get e to the negative 0.04. So I get e to the negative 0.04 here. Once again to the 5th power, that'll be e to the negative 0.2 here, divided by 1 minus the common ratio. I could multiply the 1,000 e to the 0.2 through the parentheses. I don't need to. Let's just see what this all ends up equaling here. So again, the bottom is actually the same as before, 1 minus e to the negative 0.04. What's the top? 1,000 times e to the positive 0.2 times, in parentheses, 1 minus e to the negative 0.2, excuse me, 0.2. That's the numerator of the fraction. Divide by 0.039210568. Should get something bigger than 5,000. Yeah, 5646.51. 5646.51. At a 4% interest rate, getting these $1,000 payments at these times 0, 1, 2, 3, and 4 is equivalent to getting this amount of money at time 5. Okay, if it's this 4% interest rate, that is the going interest rate for your investments. Now, of course, in real life investments, well, they all vary in their interest rates, and they also vary in their own individual interest rates over time. So these are always just approximations. All right, on to tests for convergence for sequences and series. Use the integral test to see if this series converges or not. You'll need integration by parts, show your work clearly. These terms are called an, and for the integral test, I need to find a function f of x so that f of n equals an. So actually choosing f of x is easy. N, which is decreasing over the interval, n starts at 1 here and goes to infinity. The n is discrete, but x itself is continuous. If you graph this function, you'll see on your calculator it looks like this, and it's actually got a maximum at 1, so after 1 it is decreasing. You can check that with your calculator. F of x decreases. And what the integral test says is that this series is going to converge or not. It will converge or diverge exactly when the improper integral of this converges or diverges. If the improper integral, the corresponding improper integral of this converges, then this series will converge. If the corresponding improper integral for this diverges, then this series will diverge. Hope that makes some intuitive sense. I'm not going to prove that. So we need to do the improper integral of this function and see if it converges. Hopefully you've had a little experience with improper integrals before this point, and you might remember, in fact, that the improper integral of a function like this, some power of x times an exponential decay, will converge. This is going to converge, and therefore this series will converge by the integral test. But we should be careful here, be a bit extra picky about things, and write this as a limit. That's what I want my students to do, at least. To do this integral, you'd want to do integration by parts. U equals x, and, well, you could write it as a dv equals e to the negative x dx, or as the textbook my students use, writes it v prime equals e to the negative x. You will have to find u prime and v. U prime is 1, or equivalently du is dx. To find v, you have to integrate e to the negative x. You get negative e to the negative x. So we use the integration by parts formula now. U times v is the first term. That's x times negative e to the negative x. So I get negative x e to the negative x, and I can go ahead and put 1 and b here like that. I don't have to change limits of integration with integration by parts. If I were using substitution, I would have to. Minus the integral of v times u prime. Product of these two things. That minus sign will cancel with this minus sign to give a plus sign. Oops, this is a 1 here. And then go ahead and continue. Plug in the value of b in 1 here. I get negative b e to the negative b minus negative 1 e to the negative 1. And then minus e to the negative x from 1 to b. Taking the limit of this as b goes to infinity. Simplify. Negative b e to the negative b plus e to the negative 1 minus e to the negative b minus e to the negative 1. I actually don't really care about the value of this integral. I only care that it converges. As b goes to infinity, this goes to 0, and this goes to 0. You got exponential decays, and included times a power function go to 0. That can be verified with L'Hopital's rule, but I would certainly allow my students to just remember that kind of thing and replace those with zeros. In the end, it looks like the answer for this integral is 2e to the negative 1 if I've not made a mistake, which I might have, and I'm not going to bother checking. Let's just realize I do make mistakes. The important thing about that is it's finite. This improper integral converges. Therefore, 3 dots means therefore integral of x e to the negative x converges. Therefore, the series that we are interested in, the corresponding series converges by the integral test. And again, like I mentioned at the beginning, technically speaking, to use the integral test, you do need to know your function f of x decreases. And in fact, I forgot to mention, it's also the fact that it's positive is important as well. If you were doing a proof for this kind of problem, you'd want to write sentences. But here are is the structure of the calculation and the corresponding final conclusion there. The improper integral converges, therefore the series converges. By the way, I always emphasize with my students, when you say converges or diverges, you must include the integral sign and the summation sign in these spots, okay? If you do not include those things, if you only write that converges, you're completely missing the point of the problem. That's why you've got to include it, okay? The question is not whether or not these things converge, it's whether the series converges or not. So you have to include those things, okay? You're completely missing the point if you do not. And that'll be the last time I emphasize that in this video. Well, I suppose there could be problems where people just jump in, so maybe I should emphasize it later as well, but I won't be so extreme in my emphasis later. All right. This one, use the ratio test to help you decide whether this series converges or not. Notice the summation signs there. Show your work and clearly state your answer. Once again, we can call this thing here an. And it's definitely not clear whether this series, this infinite summation, converges or not, unless you have experience with this, because both the numerator and denominator of that fraction get big really fast. 2 to the n and n factorial get big really fast. So what happens to the fraction? Does it get big? Does it get small? Does it sort of meander through intermediate values? That's not so clear unless you have experience. In the ratio test, in general, you want to take a limit as n goes to infinity of the absolute value of an plus 1 divided by the absolute value of an. Okay, just in case your series includes negative terms, which sometimes it does. In this case, we do not need the absolute value sign because all of our terms are positive. An plus 1 is this term that you get when you replace the n's with n plus 1's. So there is an when n gets replaced by n plus 1. There is an plus 1. Divide by an means multiply by the reciprocal of this. You can write that. And again, we don't need the absolute value signs anymore because these terms are positive. When you see this, it looks kind of scary at first, but you should actually jump for joy because stuff cancels. 2 to the n is 2 to the n times 2, and that 2 to the n cancels with this 2 to the n. And n plus 1 factorial means n plus 1 times n minus 1 times n minus 2 times n minus 3, etc., down to 3 times 2 times 1, but it also can be represented as n plus 1 times n factorial. And then the n factorials cancel. So this all simplifies quite nicely to the limit as n goes to infinity of 2 over n plus 1, which does exist and does equal 0, which is less than 1. That's the key condition. Therefore, the series, don't forget the summation sign, the series converges by the ratio test. Okay. Before I go into the next problem, let me make a comment about the ratio test. It is a pretty convenient test when you've got, especially when your ANs involve exponential functions or factorials. But I should say it is kind of a weak test. There are many situations where it returns no conclusion. For example, what are called p-series, it returns no conclusion. When the limit equals 1 is where you get no conclusion. If the limit were bigger than 1, you would say the series diverges. In this case, it's less than 1, and therefore the series converges. But there are many, many situations where the ratio test gives you limits equal to 1, and therefore it's of no help. It doesn't help you conclude. The series might converge, it might diverge. You need some other test in that case. This next problem is more series. It's a 4-part problem. Briefly, well, like I said, explain your reasoning clearly to decide whether these given series converge or not. Maybe I should have said brief reasons are fine. Yeah, I could say and briefly here. I'm not looking for proofs. This is just a little note to my students. Clearly, but briefly, explain your reasoning. Okay, what's this? This is actually a p-series. It's not an exponential function in the bottom, it's a power function. It's 1 over the perfect squares. 1 plus 1/4 plus 1/9 plus 1/16 plus dot, dot, dot. Actually, I think I probably would be okay, for the most part, with my students just memorizing that p-series converge when p, that thing right there, is bigger than 1. You could say converges, you could call it by the p-series test, or because it's a p-series, with the p, the power down there, equaling 2, which is bigger than 1. When the p is less than 1, it diverges. And when the p equals 1, it also diverges. This is not the same as the ratio test. Okay, this condition about being less than 1 or bigger than 1, different things are happening here. It's a different kind of situation. So you could say it converges. If you had to give another reason for convergence, another common reason people would use here would be the integral test. Integrate from 1 to infinity, 1 over x squared, which is a decreasing and positive function. And this would be seen to converge. You write it as a limit, the limit would exist. And that would allow you to conclude that the series converges as well by the integral test. This next one is not a p-series because of the plus 1 down there. So it doesn't fit the form of a p-series. But I hope you have the intuition that if this one converges, probably this one does too. They are similar kinds of ANs. And in fact, if you want to be real formal about verifying the convergence, and it does converge, you could let an be 1 over n squared plus 1. You could let bn equal 1 over n squared, the terms for the p-series there with p equal to 2. And yeah, if these are positive quantities, you divide by a bigger number, you're going to get a smaller number. An is less than or equal to bn for all n. And they are also positive, non-negative at least, and they're in fact definitely positive. And that allows you to conclude, if you want to be formal about it in terms of writing a brief explanation, that this series does converge by something called the comparison test. You could say something like, we know either from part A or from the p-series test that this converges. And we know this. It's essentially those two pieces of information that come together to say that the series we're interested in converges by the comparison test. Okay? All right, so not really a proof, but that's the idea of the argument. And again, make sure you include the summation signs. What's this one? This could be rewritten in this way. And if this -1 to the n plus 1 were not there, then it would be a p-series with p equal to 1/2 less than 1, and it would diverge. But the -1 to the n plus 1 is in there, and if you were to write out what these terms are, it'd be 1 minus 1 over square root of 2 plus 1 over square root of 3 minus 1 over square root of 4, which is 1/2, plus 1 over square root of 5, etc. It's what's called an alternating series. Now, not all alternating series converge, okay? Just because the signs go plus minus or minus plus minus plus does not necessarily mean it converges. These things that are do not include the -1 to the n plus 1 need to form a decreasing sequence that converges to 0. Decreasing sequence that converges to 0. I'm talking about the sequence, not the summation, not the series, not the summation there. It's under those conditions that you can say that means the series converges by the alternating series test. Therefore, this thing here converges by the alternating series test. It is an alternating series. Signs oscillate plus minus or minus plus, etc. The things that are not involving the -1 to the n or n plus 1 power form a decreasing sequence of positive terms that converge to 0. In that situation, you can say you get convergence by the alternating series test. Definitely not all alternating series converge. For example, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus ... That's an alternating series that definitely diverges. Its partial sums are 1, 0, 1, 0, 1, 0, 1, 0. And that sequence does not converge. What about that one? You might say, well, maybe I'd use the integral test, and you could try that, and it probably would work, I think. But you also can just note, and this is pretty much the first thing you should always think about, even though it's in the last part of this problem here. These terms, the ANs themselves, converge, but not to 0. AN converges to 1 over 500 as n goes to infinity. Not 0. The terms do not converge to 0. That's enough to say the series with the summation sign diverges, and it's called the divergence test. Therefore, the series, the entire series, diverges by the divergence test. The divergence test can only be used to verify divergence, not convergence. If the terms that you're adding do not go to 0, there's no way the summation, the series, can converge. The converse of that is false. Just because the terms go to 0 doesn't mean the series converges, and that's why we need all the other tests. It's only when the terms don't go to 0 that it's completely obvious that the series does not converge, it diverges. Find the first three non-zero terms of the Taylor series about a equals 0 for the following functions. I want to emphasize to my students to make sure to include the plus ... for full credit, to emphasize that to get equality, you really do need the infinite series, the Taylor series here. And what is the interval of convergence? What values of x do the series converge? And that's basically based on some memorization. All right, so this one, you essentially multiply x squared times the series for cosine after also substituting x squared in place of x in the series for cosine. The Taylor series for cosine starts 1, then goes minus x squared over 2 factorial, but replace x with x squared, so we get x squared squared over 2 factorial, plus x to the 4th over 4 factorial, but replace x with x squared to get x squared to the 4th over 4 factorial. And there we have, there's the first three things we need. Let's put minus ... I said plus ... but you know, you can do minus ... too. Now distribute the x squared through and simplify. X squared minus, you can leave the factorial as a factorial or you can simplify it. I'm okay with leaving factorials as factorials. X squared squared is x to the 4th times x squared is x to the 6th. X squared to the 4th here is x to the 8th times x squared is x to the 10th. Dividing by 4 factorial is dividing by 24. There we go. There's the first three non-zero terms of the series itself, plus or minus the ... dots. For what values of x does it converge to this function? You just need to memorize that the cosine series converges for all x, and also x squared converges for all x. It's not a series. This is for all x. The interval of convergence is the entire real number line. The radius of convergence is infinity. I didn't ask for the radius of convergence here, but I could have. The radius of convergence is infinity. When I write r equals infinity, I do not mean infinity is a number. I just mean the radius, so to speak, is infinite because the interval is infinite. This one, doing something similar, we got x squared in front, but now we need the series for the cube root of 1 plus x. And that's based on something called Newton's binomial formula expansion. Let me write it up here. 1 plus x to the p power, where p can be anything. This is not about p series or anything like that. It's not about the ratio test. P can be anything here. This equals 1 plus p times x plus p times p minus 1 over 2 factorial times x squared, plus the next term would be p times p minus 1 times p minus 2 over 3 factorial, but I will stop there. So apply that now with p equal to 1/3. So we get 1 plus 1/3 x plus 1/3 times 1/3 minus 1 is negative 2/3 divided by 2 factorial x squared, etc. Multiply the x squared through and simplify. Let's see, 1/3 times negative 2/3 is negative 2/9 divided by 2 is negative 2/18 or negative 1/9. X to the, oops, I made a mistake here, didn't I? This is a 3. And this would be x to the 4th. Would the next term be positive or negative? You'd have a 1/3 times negative 2/3 times negative 5/3. I made a mistake here too. Sorry. That would, two negatives would make a positive. The next term would be positive, actually. This does not converge for all x. This equality here is only when the absolute value of x is less than 1, meaning x itself is between negative 1 and 1. And so here, the absolute value of x has to be less than 1 as well. That is the interval of convergence, and it is an open interval, not including the endpoints. The radius of convergence is 1. You think of the center of the interval as being 0. The radius is the distance between the center and either endpoint is 1. That was not asked for here, but I'm just adding it on for the radius of convergence. By the way, you should be able to modify this kind of thing. If I had like a 2x here or something, then you'd replace all the x's with 2x's. And it would be the absolute value of 2x that would need to be less than 1 in that case, which would mean the absolute value of x would have to be less than 1/2. So you should be able to handle situations like that too. Something like that comes up here. This can be thought of with binomial series. You can think of it as 5 times 1 plus 25x squared to the -1 and use Newton's binomial expansion with p equal to -1 and replace the x's with 25x squared. That is okay to do. You also can recognize this as the sum of a geometric series, an infinite geometric series. That's a little bit quicker way to go. It's a over 1 minus r, where a, the leading term, is 5, and r is, the common ratio is -25x squared. As a geometric series, you could write this as a plus ar squared plus ar cubed, etc. And so for this example, that would be 5 plus, multiply these two things, you're going to get minus 125x squared plus a times this squared. 25 squared is 625 times 5 is 3,125. I hope I got that right. And the minus sign goes away. The x squared there is being squared. We get an x to the 4th, etc. And this converges for the absolute value of 25x squared being less than 1, which is equivalent to the absolute value of x squared being less than 1/25th, which is equivalent to the absolute value of x itself being less than 1/5. That is the interval of convergence. And that would also mean the radius of convergence is 1/5. That would be an interval centered at 0 with a radius of 1/5. Yeah, just make sure I don't make mistakes here. Again, I do make mistakes, so it's possible that I've made a mistake. Hopefully not. I mean, I've fixed some of my mistakes. I'll make a note if I do make a mistake. This one, arctangent of 5x. Okay, I gave him a hint. Note that the derivative of arctangent of 5x is this, which is the answer to, which is the function in part C. Those match. So if the derivative of arctangent is the function from part C, that means arctangent of 5x is the integral of the function from part C, and so you find the series for arctangent by integrating the series for the answer in part C. Keeping in mind that you do get a constant of integration, which theoretically might not be 0, but I think in this case it is 0. Yeah, because arctangent of 0 is 0. Could write C plus 5x minus 125 over 3x cubed plus 3125 over 5x to the 5th minus ... The C is 0. Since arctangent of 0 is 0, uh, 3125 divided by 5 is 625, right? Yep, 625. This becomes 5x minus 125 over 3x cubed plus 3125 over 5x to the 5th minus ... The interval of this one is a little tricky. It could be the same as this, but you have to check the endpoints too. For the sake of time, am I going to bother checking the endpoints? I don't think I'm going to bother. I do believe when you plug in x equals 1/5 here, you do actually get convergence because you get an alternating series that converges by the alternating series test. But when you plug in x is -1/5, you do not. I'm going to go ahead and write the interval, assuming that's the case, to say the interval is x is strictly greater than -1/5 and less than or equal to positive 1/5. But for my students, if you put a less than sign there, I would not count it as wrong unless it was a problem where I was telling you make sure you check the endpoints. The radius of convergence is the same as the radius from part C. It's 1/5. Okay, it doesn't matter whether you include that endpoint or not. The radius is still the same. you should keep in mind that you do technically need to check the endpoints. And if your teacher tells you to check the endpoints, then make sure you do. Almost done. Okay, this is the last main problem before we get to the actuarial science problem here. And I know this has been a long video. Oh, I need another drink. All right, looks like we have an alternating series here. And in fact, I say it converges by the alternating series test. Part A, find and simplify S3, the third partial sum. That is the sum of the first three terms. Or if you start k at 0, it would be until k is 3, typically is the way to think of that. Which would really be 4 terms in that case. But we can't start at 0 here because otherwise we'd be dividing by 0. You think about this is going to be 1 minus 2 cubed is 8. Plus 1, 3 cubed is 27. And it's fine if they do that in their calculator. If you want to get a common denominator of 27 times 8, you can as well. 27 times 8, 216. 216 minus 27 plus 8 over 216. This minus that's going to be 189 plus 8 is 197 over 216, if I have not made a mistake. Yeah, 197 over 216 is about 0.912037. 0.912037. That's a partial sum. It does not equal the infinite series. It equals this partial sum, which is just the first three terms being combined. Though it is pretty close to the actual answer already. Part B says, from the error-bound theorem for series that satisfy the conditions of the alternating series test, find an upper bound for the absolute value of the error in using S3 to approximate the sum. So that's not looking at the absolute value of this minus this. It's using a theorem. The error-bound theorem that says that for alternating series like this, the absolute value of Sn minus S, which is the absolute error, there's the approximation, there's the actual value. You can also write this in this way because of the absolute value signs, is less than or equal to An plus 1, which is not necessarily the next term. When you use this notation, it's common here to think of this as this term as -1 to the k minus 1 times 1 over k cubed, and call this thing the AK. When it's an alternating series, that's a more common thing to do. So it's different than usual. AK is not the kth term here for the alternating series. It's -1 times to the k minus 1 times AK that is the kth term. But if you use this notation and let AK be the 1 over x cubed, then you don't need absolute value signs here. You can just write An plus 1. So the error-bound theorem would say that this is true. When n is 3, that would be A4 here. But what is A4? It's what you get when you plug in k equals 4 here. 4 cubed is 64, so this is 1/64. The error-bound theorem guarantees that the absolute value of our error is less than or equal to 0.015625. Now, the actual absolute value of the error could be smaller than that. In all likelihood, it is smaller than that. S3 minus S, by what we found earlier, is approximately the absolute value. Here's S3, 0.912037. S is up here, 0.901543. In all likelihood, this number is less than this number. .912037 minus 0.901543. Already positive, so the absolute value of it is itself 0.010494 is the more precise, more accurate error, which is what the goal of this problem, actual error, it is less than or equal to this, as it always is, because that's what the theorem guarantees. Sometimes it might even be significantly smaller. It's possible. Okay, so for my students here in spring 2020, you can stop there. But for other students in the future, I want to do one more problem that's related to actuarial science and probability and is pretty tough here, tough looking at least. It's not as tough as it looks actually. It's just long, and if you haven't learned this material, it's like, whoa, how in the world am I going to get my mind around that? So again, if spring 2020 has been shortened, so I'm not requiring my spring 2020 students to know as much as usual for the course. But let's do this problem anyway. T is what's called a lifetime random variable. It's a quantity that can represent the lifetime of something, a person, an appliance like a refrigerator, etc. It's got something called a uniform distribution over this interval, which means its probability density function is this function here. It's a graph that's a horizontal line at 1/50th when t goes between 0 and 50. And effectively, the fact that that's a horizontal line means the chances of the refrigerator, let's say, failing during any small amount of time doesn't depend on the current age. It's constant for that small amount of time, with that graph being horizontal. Let z be 1,000 minus or times e to the negative 0.02 times t. That's the present value random variable of a $1,000 payment made t years from now. It's like a warranty. Okay, the refrigerator fails within the first 50 months, say, you get a $1,000 warranty payment. And this is variable z represents its present value as a random variable because you don't know when that refrigerator is going to fail. Assuming a 2% interest rate. So we're thinking about present values again, so we got to think about interest rates. Let g of z be the CDF of z, cumulative distribution function. All this stuff is just an elaboration on how to find the formula for g. You don't really need to know it for the purposes of doing the problem. You only need to know the final answer. With my students, I emphasize this when I have time, at least in a semester where I have time, over and over and over again, so this, even though it's confusing looking, is not something they haven't seen before, so they can glance over it quickly. Part A, let little g of z be the PDF of z, not of t, but of z. Find a formula for little g. Its domain happens to be this, but don't worry about that. Just to do this, all you need to do is use the fact that you should know, if you've studied this, that the PDF is the derivative of the CDF. So to do part A, it's really pretty easy. Just differentiate. Differentiate this or this. And the answer is pretty quick. These are constants. It's 1 over z. There is the PDF for z, this random variable that's representing the present value of the future $1,000 warranty payment. And it's a function that looks like that over the interval, which happens to be 1,000 over e to 1,000. And it is a probability density function. You can check the integral of this as 1 over this interval. And what this is saying is the fact that the graph is higher at low values and lower at high values of z is for small intervals of z, small intervals of present values of the future $1,000 payment, you're more likely to have a relatively small value of z than a large. It's because of the exponential nature of the compounding going on. That's why that happens. Effectively, that's also saying you're more likely to, with that compounding, the present value is more likely to be small, the later death times of the refrigerator, failure times, are way more heavily on the present value because of compounding. Part B, find the probability that z is between 800 and 900. You integrate the PDF, but you don't have to do that integral here because, hey, we have the CDF. Well, we're doing the integral, but you don't have to figure out capital G because it's already given to you. Capital G of 900 minus capital G of 800 is the calculation to do. The constant terms will cancel. You'll get natural log of 900 divided by minus natural log of 800, which by properties of logarithms is natural log of 900 divided by 800, which is natural log of 9/8. This probabilities have to be between 0 and 1, and this should be. Yeah, natural log of 9 divided by 8, about 0.118 is the probability that the present value of the future payment will be between 800 and 900 for this random person who just bought your refrigerator and you don't know when their refrigerator is going to fail. Part C, find the mean of z. So you need to integrate z times g of z. In fact, it's kind of like a moment. In fact, it's often called a moment in probability. Over the entire interval here, 100 or 1000 over e to 1000. Fortunately, it's a simple integral to do because z and g of z, the z's cancel when you multiply and you just integrate 1. 1 dz. So you get 1000 minus 1000 over e, which is also 1000. E minus 1000 all over e, and you can factor out 1000. Yeah, e minus 1 divided by e times 1000. Looks like the mean's about $632. That's the mean payment on the warranty over many, many customers. Mean present value, I should say, sorry. So that's useful because it tells you how much money you should set aside as a company, the refrigerator company, to cover these warranties, how much you should set aside per customer on average right now. Very last part, find the median of z. Median of z. Okay? Part C was to find the mean, part B is to find the median. You integrate z times the PDF to find the mean. For the median, you just figure out where does the CDF equal 0.5. Half the probability is to the left of that value of m, half is to the right. M is a value of z that's going to be the median. I'm calling it m for median. This is what's called, excuse me, what's called a right skewed distribution. Oh, and I'm out of water, almost. Right skewed, it's got a long right tail. The mean is going to be bigger than the median. We're going to get a number less than 632 here. So this is just a matter of using the formula for capital G and solving for z. 1 minus natural log of 1000 plus natural log of, I could call it z, but I'll go ahead and still call it m, equals 0.5. It's natural log of m. Subtract 1, 0.5 minus 1 is negative 0.5, add natural log of 1000. So natural log of 1000 minus 0.5. Exponentiate, it looks like m is, using properties of exponents, 1000 e to the negative 0.5. If I've not made a mistake, always get that caveat here. 1000 times e to the negative 0.5 better be less than 632. 606, yes it is. 606.53. So half the refrigerators' present values of their warranties are going to be smaller and half are going to be bigger than that. More important is probably the mean because that tells you on average how much money you need to set aside and invest really to be able to cover these warranties when those refrigerators fails. That's pretty long. I'm pretty tired. Thanks for watching.